Look at this video for the setup that I will be using in this. There is a link in the text for this video. Here I have the 3 HF Plus units running with the latest library of August 22, 2018. It's just the antenna signal now, plus the reference signal on 7.19778 megahertz. It is at minus 118 dBm and the S meters are properly calibrated on it. Now I will switch on the signal on the image frequency, like that, and you can see it here, here, and here, and after a fairly short time it becomes rather weak, or very weak. I can show very clearly the effect of the IQ balancing by changing the frequency from 7 to 5 megahertz, and then I change it back. You can see the mirror here and the time it takes for the algorithm to figure out how to balance it out. And on this unit it's very much the same. And also here. And you can see not only the generator but some other image things disappear. Almost. Now this operation is now with the default parameters for the image rejection. But that can be changed, and I will change it to demonstrate the effects of doing it differently. In the Linrad setup there is an option, set non-default IQ balancing. Yes. I can say buffers to skip 0. This means the CPU load will be bigger, but the response will be more accurate. And then FFT integration, it's default 4. So I leave it by 4. FFT overlap 2. That means that twice as many transforms are computed as when you set overlap 1. Cost CPU, I say 2. And then correlation integration, default is 16. Now the accuracy improves if the integration is larger, but for this setup I want a faster response while retaining accuracy, so I make this, let's say, 4 only. And then XX and save this and go back to the processing here. 7.2 megahertz, and here is this signal. Now I go the 2 megahertz stepping and then go back, and you see this is much faster, and it is also at least as accurate. Now accuracy is a different problem. It matters in some specific situations, and normally, like you can see here, there is no trace of this mirror image signal. But looking here, the workload, it's not bigger actually. I expected it to be a little bit bigger than what we have here. Well, now assuming I am on a very low capacity computer, a Raspberry Pi or something, and maybe I want to run several instances of the program with the hf+. So I set parameters that are very low on CPU load. So I say buffers to skip, let's say 8. FFT integration, I make it only 2. And then overlap, I make that 1. These two parameters are related and shouldn't really be two different ones, because if I say there is no overlap, the buffer contains only 2 transforms. But if I say overlap, then I can make 4 transforms from the data. Setting other parameters will not cause any problems, but might not give the result that you would expect. And then correlation integration. I want good accuracy, even though I have degraded computation, so I leave that at 16. And then I said Z and X, and save this, and so on the frequency here you can see it takes some time for the image to not quite disappear, but to become much lower. And the CPU load 4.6, 5.7. And I think I have to wait for a while, and it will become eventually as good as before. So this depends on what you are doing. Is it necessary for the IQ balancer to get adjusted to a new frequency fast, or is that not important at all? And here I set the parameters for best possible performance, not for the fast time response, but to suppress the image best. And assuming I have a PC or something with good computing capacity. So buffers to skip is 0. FFT integration is 4. Because that's the most we can have considering the buffer size. So this has to be 2. And I set correlation integration to 6 to 32. It doesn't have to be a multiple of 2, but I generally like to do it that way. And then save this and look at the result. 7.2, and I have to click on this pilot tone, the reference signal at -118 dBm. Now I step downwards 2 megahertz and then up back. And here you can see the time it takes and the level we get down to for this image. And it isn't significantly better than what we had here, but this one is not quite as good because we are saving CPU time here. It's 4.45, this is 5.69, and this is 5.79. So on this kind of computer, this is a fast one, an i7, the CPU load of the things done in the library is totally insignificant. Now, to evaluate the what is the signal level of this? To see that better, I changed the resolution of the baseband in Linrad. Like this. So here you can see the mirror signal, and to get an idea how strong it is, I cannot just click on it because it's in the noise. Well, if I do, I then have to set the bandwidth much narrower, and I would say this indicates the level is minus 135, and I switch it off, and you can see the noise level is about the same. So this is not an accurate measurement of the level of the signal. I can try to make the resolution even a little bit higher. These things go much slower. Minus 18 maybe. And 1 here. And now I can set the bandwidth narrower. So we are on this image signal here. And I switch the generator off. And it goes down by maybe 6 dB. So we can say that, and you can see an interesting thing is this image, although the signal at the image frequency is a perfect narrow band sine wave, here because of the balancing function, which varies all the time, the signal is modulated and it's spread out over a bandwidth of, well, it is 100 hertz from here to here, so it may be 5 hertz or something like that. Anyway, the image is at about minus 135 dBm. And the signal at the image frequency is here. Well, it's not so easy to find it. Here it is. It is at minus 30 dBm. And I switch the generator off just to certify that that is. So the mirror image rejection is 105 dB, or a little bit more on this with these parameters. That is pretty excellent, I think. And of course, it is not quite as good here, but the difference is very small. I now increase the signal at the mirror frequency by 10 dB. And it goes up by 10 dB here, which means the AGC did not do anything. But here, the signal level has dropped by 10 dB on the, what do you call it, on the reference signal I have. So the AGC works differently. This is the 1.7 something firmware, and this is the 1.2 firmware. I go back to the mirror image frequency here, and try to find is this image spur. This is the reference signal. Well, I have to decrease resolution. Here it is. Now it's more clear how this signal is modulated and what the spectrum is like. It has a sharp, but not so sharp here, and it's some certain width. And the signal on the mirror image frequency is now minus 20 dBm, but the interference I get from the image is at minus 100 and let's say 28, which means now the suppression is 108 dB. And here AGC has turned it down, so the scale is wrong by about 10 dB. And we can see the image much stronger here than it was if I go back to normal parameters here, 11 and 5, and let's say 5 here. No, well, it doesn't look much different. So this gives an idea on that the wideband image rejection routine within the AIRS by hfplus library gives far better suppression than you have in most other direct conversion receivers. Take for example Linrod with the WSE converters. You can get something like 70 dB or so, maybe 80 if you're lucky, and the temperature is stable and everything. Now that is adequate for that hardware because the limitation is the overtones. When the audio frequency is, let's say, 5 kilohertz, you have audio overtones at 10 and 15 and 20 and 25 kilohertz that create spurs with phase relations that are absolutely not compatible with any rejection algorithm. So it's because those nonlinearities are not present in the hfplus. That's the reason why a much better IQ balancing routine is really useful. I have removed the antenna signal and added a frequency modulated signal which covers a wide range like that. The modulation frequency is 400 Hz, so this signal is carriers separated by 400 Hz. You can see the difference between the hardware. Here there is quite a lot of image, particularly at the edge, but at the frequency I have selected to listen to, the suppression of the image which you have up here is very good. Now I can click out here and you can see how the balancing routine suppresses the image here, but it's no longer so good back at 7.2. So I go back to 7.2 here, and after a while it is well suppressed here. and not out here. Now this unit is a little better, and this unit here is much better. The balancing function depends on the frequency differently in different units, and this one happens to be a little better on 7 megahertz. In strSharp there is a file strsharp.exe.config. That file allows setting the IQ balancer parameters here: buffers to skip, FFT integration, FFT overlap, and correlation integration. And these are the defaults today in version 1672. That's the same library that I showed in Linrad. Here I have the 3 HF Plus units running and the parsers. I have only a signal on the mirror image and a signal on a desired frequency. Here, a weak one, minus 118 dBm. I turn up the level on the image frequency, and you can see there is something and it disappears quickly. Now the different units don't differ very much. At this point, the IFAGC starts to do changes, so I step back like here. Now, this is without any other signals. I add the antenna signal, and you can see here there are problems because this unit doesn't have the preselector. This unit has the AGC, and here there is the preselector, so AGC is not affecting the result. I mean, this one and this one use manual gain setting. So I have to reduce the antenna signal like this, and all looks pretty good. Also, this old software version. I now simulate a crowded band situation by using 2 FM modulated generators, this one and that one. And they produce a huge amount of carriers spaced by 400 Hertz, which is the modulation frequency. That is what the IQ balancer experiences because it uses a Fourier transform. Actually, in the time domain, it's just 2 signals that are present, but they are frequency modulated. What I see in the HF Plus units here, the desired signal isn't really visible anymore. I will first, let's see, I go for the parsers, which is a kind of reference, and then I look for the signal to noise ratio, which shows about 0 on the signal to noise evaluation track, the yellow track here. It's plus 0.5 dB. Then I go for the old firmware and software, and I switch off, of course, the parsers, and I have to reduce the level of the antenna signal until I can see the desired signal. Sorry, I don't have any antenna signal. I have to reduce the level of these signal generators until I have a reasonable signal to noise ratio on the desired signal. Here it is half a dB below what I had in the Perseus. Well, I have only 1 dB stepping, so the level I have to set to lose about 3 decibels. That is 52 decibels on this attenuator. With the latest firmware and software, I get about 0, and I turn on more signal. You could hear the image come up for a short while and then disappear. Here there is a problem. This is the level I have to set to get a 3 dB degradation. And this is 17 dB on the attenuator. Compare that to 52 dB. That's the improvement in this situation from last year's software to today's software. I now switched to the second unit running 1672 SDR sharp, and as it happens, it seems very much the same. I reduce the antenna signal generators, and well, the level is minus half a dB, so the loss was not quite 3 dB. To get the 3 dB loss, I have to go here, no, here. So that is 16 dB. Now I am listening to the Perseus, and I turn up the level of the signal generators by 10 dB. And that's not acceptable. So here is the level I can set for a 3 dB loss with the Perseus. And that is 9 dB on the attenuator. There is an interesting phenomenon in these direct conversion receivers. I turn the level of the signal on the image frequency down, like this, 10 dB, 20, 30, 40, 50, and here suddenly we can see the signal on the mirror image frequency. And I go down one more 10 dB step, and it becomes fairly strong both here and here. Now the signal is not so strong, and the signal on the image frequency is fairly strong compared to that. The rejection is really poor now. The reason is that the A to D converter causes quantization errors. if the DC level happens to be at the midpoint between two levels of the AD converter, then the amplitude that comes out on the digital side is different as compared to when the DC component is on one of the levels. And the latest version of the firmware doesn't, in this case, compute the corrections from the incorrect data that comes from quantization errors, although the old version is doing that. What I can do here is to add a second signal to produce some dithering. Now I added a second signal with the same amplitude, and it doesn't make any difference, but I increase it. And now it's about 10 dB stronger, and it causes the image to disappear. Because the dithering signal now sweeps the AD converter over a wider amplitude range. In real life there would be antenna signals, and they would sweep the AD converter over a significantly larger range, and that would eliminate the problem. This is a problem we see in the lab while using signal generators. And it's not very significant in the HF+, but with this algorithm on, let's say, an RTL SDR with an 8-bit AD converter, this is a much more significant phenomenon.